study of the relationship between chemical reactions and electricity. There are basically two main ways that chemical reactions and electricity interact, and in order for us to investigate those reactions, we usually use electrochemical cells. These electrochemical cells are used to investigate chemical reactions that involve the movement of electrons, and those reactions tend to be redox reactions. In any redox process, oxidation is the loss of electrons, while reduction is the gain of electrons. After the reaction, the reducing agent or agent of reduction is the oxidized substance and ends up with a higher oxidation number, while the oxidizing agent or agent of oxidation is the reduced substance and ends up with a lower oxidation number. One of our most famous chemistry mnemonic devices for redox is Leo the Lion says GER, where Leo stands for lose electrons equals oxidation, while GER is gain of electron equals reduction. Now, a more complete version of these is Leora-Geroa. Leora for lose of electron is oxidation of reducing agents, while Geroa is gain of electron for reduction of oxidizing agents. As we have mentioned earlier, there are basically two main ways that chemical reactions and electricity interact. Certain chemical reactions can generate electricity, while for some, electricity can make certain chemical reactions to occur. The electrochemical cell which generates an electric current are called voltaic cells or galvanic cells, while those that generate chemical reactions are called electrolytic cells. These electrochemical cells consist of two conductors called electrodes, either a cathode or an anode. Cathode is the electrode at which reduction occurs, while anode is the electrode at which oxidation occurs. For this one, a good mnemonic device is a red cat and an ox, reduction in cathode and oxidation in anode. Or you can also use vowels and consonants. C and R are consonants, while A and O are both vowels. For both cells, electrons flow from oxidation half cell to the reduction half cell, that is, from anode to cathode. The charges of the electrodes are determined by the sources of electrons and the direction of electron flow. Notice from the setup that we have two electrodes dipped into an electrolyte. These electrodes conduct electricity between cell and surroundings. In a voltaic cell, electrons are continuously generated at the anode, and so it has an excess of electrons relative to the cathode, generating a potential. Thus, the anode is negative relative to the cathode. In an electrolytic cell, the electrons come from external power source. This source supplies electron to the cathode, connected via the negative terminal of the power supply, and removes them from the anode, connected to the positive terminal of the power supply. Thus, the cathode is negative relative to the anode. In general, voltaic cell uses a spontaneous chemical reaction to generate electrical energy, while electrolytic cell uses electrical energy to drive non-spontaneous reactions to occur. A good mnemonic device for this one is, the next time you see an electrolytic cell, don't panic. Don't for non-spontaneous reaction, P is positive and A is anode. So you have to have a positive anode and NiC for negative is cathode. So remember, don't panic. Recall that in a voltaic cell, the free energy change of a spontaneous reaction is converted to electrical energy. This electrochemical energy is proportional to the difference in electrical potential between the two electrodes, which is called the cell potential or E cell, also known as the voltage of the cell or the electromotive force or EMF. Recall that electrons flow spontaneously from the negative to the positive electrode. That is toward the electrode with a more positive electrical potential. Thus, when the cell operates spontaneously, there is a positive cell potential, and in the same way, E cell is negative for a non-spontaneous cell reaction. If the reactants and products are in their standard states, that is 1 atmosphere for gases, 1 molarity for solutions, and pure solid for electrodes, we obtain a standard cell potential or E naught cell, which is measured at a specified temperature, which is usually 298 Kelvin. E naught cell is the difference between the standard electrode potential of the cathode and anode half cell, which is given by the equation E naught cell is equal to E naught cathode minus E naught anode. The standard electrode potential, or E naught half cell, is the potential associated with given half reaction when all the components are in their standard states. By convention, half reactions are written as reductions, as shown in this example, and the values are relative to that of a standard hydrogen electrode, or She, with standard electrode potential defined as 0 as stated in the PACT sign convention. As mentioned earlier, the term electrode potential is used to describe half reactions, written as reductions. The sign of an electrode potential is determined by the sign of the half cell in question when it is coupled to the standard hydrogen electrode. Consequently, when the half cell of interest exhibits a positive potential versus the She, it will behave spontaneously as the cathode. When the half cell of interest is negative versus the She, it will behave spontaneously as the anode. A list of these electrode potential values for selected reduction reactions at 298 Kelvin is shown here. The more positive standard reduction potential, the more readily the half reaction occurs as written. Since the half reactions are written as reductions, reactants are oxidizing agents, and products are reducing agents. Therefore, the strength of oxidizing agent or the reactant increases going up, and the strength of reducing agent or the product increases going down. Thus, using this table, the best oxidant is chlorine, and the best reductant is zinc. In general, this list in principle is the basis of activity series of metals. Activity series rank elements in order of ability to displace each other. Metals that lie above hydrogen are stronger reducing agents, since a more reactive metal can displace or reduce hydrogen ion, or the ion of a less reactive metal from solution. For example, silver is considered less active or weaker reductant than copper, since silver is found lower in the list. Moving on to some applications, specifically of an electrolytic cell. Electrolysis is the splitting of a substance by electrical energy input. Practical applications of these processes include recharging a battery, electroplating, and electro-refining of metals. Thank you so much.